Say yes. Okay. So, I've mostly today we've been hearing about all the different data we have and the things that we know. I am mostly going to be talking about things that we don't know. Calving is a fairly young discipline of glaciology. The sort of oceanic side of it is even younger. So most of what I've structured this around today is questions, things that we don't know that we would like to know, and I guess I would like to hear from you guys about how we can go about knowing them. Also, I've changed it. I was asked to talk about oceanic effects. I've changed that to aquatic effects because we're very rarely talking about oceans in this context. Usually it's fjords, which are sort of small enclosed bodies of water. Sometimes it's even lakes, which aren't even salty, and they have a completely different thing going on. So first, some simple observations, the sort of thing you can get by reading Doug's paper and thinking for a few minutes. This is a plot of, it's actually of calving speed versus water depth, and there's a sort of, no, oh no. There's a sort of fairly clear positive relationship. There is a longer one. I'm good. Thank you. So there's a fairly clear positive relationship between water depth and calving speed. I don't think that's actually that interesting. It's just sort of a scaling law. You would expect that calving speed would somehow scale with the size of the system, and that it's linear is perhaps not obvious, but also neither is it surprising. What I think is interesting here is that there's a definite relationship with temperature. So calving rates are much higher in Alaska than they are in Svalbard, much higher in Svalbard than they are in Greenland, and also they're much higher in the tidewater systems than they are in the lake systems. So the first, also, this used to appear on the first slide of everything. This was the introductory slide to every talk from about 2009 through to 11. It hasn't shown up at all recently, but this is from David Holland's paper from 2008, showing how warm water crept up the side of Greenland and probably initiated the collapse of the floating tongue at Jakobshavn Isbrae, which is sort of in the sort of late 90s, early 2000s, which led to speed up and the usual thing. So the first question, which I would like to know the answer to, is this: why do things calve more in warm water? This is a question. It sort of seems really obvious until you think about it, and then it stops being obvious, and then you have to think about it a whole lot more before it becomes obvious again. It's sort of, you expect ice to break up in warm water, but the reasons for that are not clear. Ice actually becomes less brittle as you heat it. As any solid approaching its melting point, it starts to stretch and stuff rather than becoming brittle. Generally, if you wanted to break something, you would cool it down. So it should be harder to crack ice in warm water. But instead, we see a rather enhanced calving in warm water. So I think a comprehensive answer to this would go a long way towards helping us with an understanding of calving. The obvious answer, of course, is that it's melting. But generally, we think of calving and melting as quite separate processes. And so I think it's very interesting that we get more calving when it's warm. Similarly, why do tidewater glaciers calve so much more than freshwater glaciers? Going back to the plot, you can see that, okay, the relationship, the slopes of these things are different, but also all of these are calving way more than all of these, even for these guys out in Patagonia, where it's plenty warm, there's plenty of surface melting, but because they're going out into lakes, they don't seem to calve at the same kind of speed that their friends in Greenland or Alaska do. So once again, you might say, well, this is a melting phenomenon, that there is a lot of salt in seawater, and salt tends to melt ice. There's no salt in fresh water, so the ice doesn't melt so much. So let's have a look at how frontal melting works. So this is a fjord. Um, the general conception that we have in glaciology of fjords is that they are big blocks with a possible sill at the end, and that you've got a glacier. Cold water comes out from under the glacier through some sort of subglacial discharge process. This sort of mixes with warm water. This stuff is cold and fresh. This stuff is warm and salty. This stuff is buoyant, so it starts to rise. It entrains this stuff, and so we get warm water moving quickly up the front of the glacier, and that leads to melting. Now, in order to measure this, what we typically do is a heat flux calculation. So this here, I mean, I haven't drawn it in, but here is a very dangerous place. You can't get up close, you can't make direct measurements. So what we generally do is we put a boat somewhere about here, and we take some CTDs. And we also take velocity measurements. And if you've got measurements of temperature, salinity, and velocity, you can do a bunch of conservation arguments. You can use salt conservation to work out how much water is coming out from the glacier. And then once you've got estimates of how much water is coming out from the glacier, you can use a heat conservation argument to work out how much melting is going on. And lots of people have done that, going back to, I think the first was Roman Matika in 2003. And you get, these are some of the kinds of numbers that you get. So in Alaska, people have been getting numbers up around the sort of 10 to 20 meter per day mark. That's typically around about the scale of the ice flow velocities in these places. So in Alaska, your ice flow is being balanced by frontal melting, at least on these glaciers which have been studied. Obviously, it's a small subset of the glaciers in Alaska. Might be interesting if someone would do this at Columbia, if we're all going to be studying Columbia, so that we know whether we're actually looking at a melt-dominated system. In Greenland, the numbers are generally smaller. This is the other big area where it's been studied. This makes sense. The water there is a lot cooler. The one I would like to point out, now I'm not sure if anyone's seen this paper because it came out in JGR Oceans about a month or two ago. An estimate of 10 meters per day of melt at Kangerlussuaq. That's about half of the flow speed of Kangerlussuaq, which is a major outlet of the Greenland ice sheet. I was shown a copy of this paper before publication and asked to look over it for submission, rather. And the first thing I saw was that number, and I thought, that's ridiculous. That's not right. And then I went through the paper, and I cannot see what is wrong with this number. So I think the difference between this and Helheim, which is sort of the glacier 2 doors down, generally considered quite similar. I think that's a huge issue.
Can I ask, I mean, these glacial streams are usually coming out at one point, while the ice is kilometers wide or so. Is that a point to discuss?
That is a point to discuss. I will discuss that at the appropriate time. All of these numbers are all averaged across the front. At the moment, we don't have point measurements. So what we're actually getting is a heat flux, which we divide by the assumed area of the ice front, and then you get something, which is, we generally translate these into melt rates in meters per day, but really what we're talking about is joules. But yeah, I think the distinction between this 2 and this 10 is definitely something we want to get into if we're going to understand how all this heat goes.
Are those made in the same time of year?
These are all made in summer because that's the only time you can get a boat up there.
The same time of summer?
Roughly sort of July to September, typically. I mean,
like Tim's paper says that July would be very different than September, so.
Absolutely, yeah, I think that's right. But these are all broadly similar times of year. I think in most of the big Greenland fjords, there is only maybe a month that you can get a boat up them. So these are fairly comparable. I mean, it is possible that there's an explanation here, which is that different things are happening at different times of year. If that is the case, then it could just be that the different glaciers are out of phase. So even if we looked at them at the same time of year, we would see different response anyway. If someone wanted to go out and do a study where we did this repeatedly at different times of year, that would be great. I think that would be an enormous logistical challenge, but I'm not much of an observationalist, so what do I know? Anyway, so moving on to this, the first question I have about this is, can we independently verify these? I sort of expected there'd be more oceanographers here who I could ask this question to. I think I'm probably the closest thing to an oceanographer in the room, which is deeply disturbing. So it would be really useful to get independent verification of these heat fluxes, because at the moment we are inferring from reasonably distant measurements through a slightly convoluted process what these melt rates actually are, when it would be nice to have some measurement. I mean, even if we couldn't verify them in every case, if there was one or two cases where we could get an independent measurement that corroborated these, I'd sleep a lot better at night. Another question is, as Jeff rightly pointed out, can we measure the distribution of these things? At the moment, this method is producing an average melt rate across the front. That's sort of useful and all, but it doesn't really tell us a lot about the physical processes that are going on. So I think this would be really useful. If anyone has any clever ideas about observational techniques that could give us this, I'd like to hear them. Some people have looked at doing sonar. I know Eric Rigno's group have taken some side scan sonar. I think Alan Hubbard's group have done the same. Repeated surveys like that might give measurements of distribution, but I'm not 100% sure. So moving on from that, I want to talk a bit about how we model these things. I'm a modeler, this is what I do. So again, this is our diagram of what's going on. The process, cold water, warm water, outflow. So the first models of this were I'm going to call them analytic models because they're a simple differential equation. We don't actually have an analytic solution to these models. But essentially the idea is that you have a flow moving upwards, which has a particular velocity and cross-sectional area and salinity and temperature at a particular height. You have water coming in from the outside, which is warm, water coming out from the ice, which is cold. So cold and fresh, so warm and salty. And you can write down some equations for these. These are a little bit scary the first time you see them, but actually what we're always saying here is that we have conservation of mass. So velocity, the rate of change of velocity times area is equal to entrainment plus melting. We have conservation of momentum, so this is a momentum term. This is a buoyancy term, and this one is a drag term. Conservation of heat, so this is the heat transport being it's a balance between entrainment from the ambient temperature and the melt, which has a complicated latent heat thing going on, but is essentially just cooling from the ice. And we've got conservation of salt, which is very simple. The only way you can get salt is by entrainment, so it's entrainment times the salinity. So this is pretty simple. There's not much you can do to change this. There are a few bits of this which obviously don't have expressions here. We need an expression for how much entrainment is going on. We need an expression for how much melt is going on. This is a term which will come up again. This is the length of the boundary of the plume, which is in contact with the ice. Similarly, you'll see a big CW, which is the length in contact with the water. And you can do a lot by playing with those. So what we generally do is we say that entrainment is proportional to some constant times the velocity times the surface in contact with the water. We say the surface in contact with the water is approximately equal to the surface in contact with the ice. The other way around. And that scales roughly like some power of the area of the cross-sectional area of the plume. If you set that P to 0, that just means that the plume is rising as a plane. If you set that P to a half, then that plume is rising as a sort of circular thing. You can set that, of course, to other values between 0 and a half, or even outside that range if you feel a little crazy. from my own work, 1/4 works well, which is essentially just taking the two extreme members and averaging them. Um, then this is the melt rate parameterization we use. It's pretty scary looking, but essentially you've got two numbers you can plug in, one of which is the thermal Stanton number and the other which is the diffusive Stanton number. These are numbers which the ice shelf people have worked out a long time ago. So the numbers we use are generally derived from ice shelf calculations. So we're generally a couple of order of magnitudes different in our velocities and so on from them, but we're still using the same numbers. So it would be interesting to know if those numbers are actually right in our context. There's no reason why they shouldn't be, but these numbers have been tuned to a very different situation. So the general point about this analytic model is that it is simple. It is not obviously wrong. It's probably wrong, but there's nothing in there which obviously produces ridiculous numbers. And when you do these calculations, you can generally just about match the observations in terms of peak melt rates, but you're getting way too low numbers on average. If you assume planar flow, you generally get slightly better matching on average, slightly less good matching on the peaks. So the other approach to this problem is to run a GCM of some kind. MIT GCM is popular, also fluidity is picking up. This produces very pretty pictures and not much else. So a lot of people have been doing this. There's, I think off the top of my head, I can think of 5 or 6 groups who are running models like this. They all seem to be getting very similar answers because they're all doing very similar things. I'm not sure exactly how much we expect to learn from this. So overall, I think these things are a bit big, complicated, fiddly, and slow. They are more flexible. You can do things like look at what happens when you have 2 plumes next to each other, when you have a plume on a curved surface, when you have real topography, and so on. You can also maybe extend them a bit more easily to connecting to fjord models. I have seen some work very recently by Tom Cowton looking at using an analytic model as a boundary condition to a fjord model, but that's still at the very early stages, I think. So looking at this stuff, one question is what's the right shape of plume to use in an analytic model, and can we generally represent this as an analytic model with some kind of shape function? If we can, that's so much easier because these run at considerably slower than real time. If you want to simulate a minute of a plume, it takes hours of supercomputer time. So doing this this cannot be what we are doing in the long run. It's one of those things where possibly we might be better off waiting for our computers to get better and then running our models. So we're going to have to simplify this. So I think the analytic models are really the direction we want to be moving in my opinion. Maybe others differ. But in that case, we're going to need to work out what that shape function should be. As I said, the quarter thing works quite well, but we'll see. And the other question is, what does the subglacial hydrology look like? This is something which subglacial hydrology people don't seem to have looked at very much up until recently. I know Ian Hewitt had a poster at the recent IGS symposium on this, but the subglacial hydrology in a sort of submarine environment isn't something a lot of people know very much about. I don't know of very many studies, either modeling or observational, which have gone into it. But it's very important because that's going to determine what the plume structure looks like when it starts. Ian's models seem to indicate that what we would expect is some sort of delta structure near the front of the ice, but we'll have to see. I think that was still at the early and sketchy side. And also, why are the model melt rates so much lower than observations? Is this a problem with the observations, as I suggested it might be earlier? Do we need to independently verify these observations? Or do we need to change our models? Or do we just need to change the numbers in that melt rate parameterization? You can just, if you are willing to say that the numbers are 2 or 3 times what the ice shelf people say they are, you can get a lovely match. But there's no basis for that other than trying to make your model work. So we'll see.
When you say observations, you mean frontal retreat rates?
No, I mean those heat flux calculations.
Okay.
So yeah, if you want Helheim to melt at 2 meters per day, you need a lot more heat to be transferred to the front than the ice shelf parameterization suggests should be.
How good are those heat flux?
Sorry?
How good are those heat flux calculations?
Well, I don't know. We don't have anything to compare them with.
So, how can you say one is better than the other?
Well, that is exactly my point. We can't. Sorry, which heat flux?
Well, okay, so you say the observations you get from this
Heat flux, yeah.
Yes. But how good are those estimated melting?
Well, that's the problem. I mean, the stated error numbers on those are pretty small, but that's not saying that the actual errors are pretty small.
Okay, so then how do you know the model ones are wrong?
I don't. I just know that they're lower than the observations.
So in the ice shelf world, the rule of thumb is that we can predict melt rates to within a factor of 3 and not better. Using flume models, just about anything else we throw at it.
Yeah.
So it sounds like you're kind of at that same.
We are just about. I
except
think
your observation
we're
might have
probably
errors.
more within a factor of 10 than a factor of 3. But yeah, I think given that we're quite a long way outside the ice shelf regime, we're still doing. I think it's pretty good, but Christian.
So you measure the inflow of heat, you measure how much comes out again in your outgoing surface current.
Yeah.
And then your model doesn't match that, but your model has some heat transfer coefficient, which you call something or other.
The thermal Stanton number.
Which you said comes from, well, not quite thin air, but from the ice sheet.
Yeah.
There's probably some roughness idea in there.
I mean, it comes out of sort of.
Latitude to dial things.
There's quite a lot of latitude to dial things. The question is this what we should be doing, or is something else wrong? And I am perfectly willing to entertain the idea that that's what we should be doing, but I'm also willing to entertain the idea that something else is wrong. And I think we're building a sort of bridge here between two quite disparate things, and there are a lot of places in the middle where a small error means we're not matching up. So I think what we could do with is some more struts on that bridge to continue a metaphor, and just we need some independent verifications of some of the steps in the middle so that things match up a bit better.
So the ice shelf numbers that you're talking about,
Yeah.
they all come from sea ice measurements, which you can actually quantify things a little bit better. There's really few measurements to indicate they actually work on a slope, gentle slope like an ice shelf. And now you're applying them to a vertical face. So there is a bit of a jump in what you'd expect your turbulent fluxes.
Absolutely, yeah. I don't think we're in disagreement here. As I say, it is entirely possible that everything is fixed by changing these numbers, but it's also possible that it's not. For all we know, that these numbers should be an order of magnitude the other way. So yeah. Any other questions before we move on? Objections? Okay, so I'm going to talk a bit about fjord circulation, because this is what sort of drives the ambient waters, which then drive that plume thing. I don't want to get too far into the oceanography of this, because that's a whole other field and it's not really mine. But this circulation, which I've drawn here, this is sort of the thing an oceanographer would call an estuarine circulation. So you've got fresh water coming out here, and so fresh water flows out at the surface, salt water comes in at the bottom, and you get a circulation like this. That's one of the possible circulations that you can get. And it's sort of the obvious one from a glaciological perspective because it's being driven by the glacier. The other is what an oceanographer calls an intermediary circulation. This is what happens when we have along flow winds, winds flowing into or out of the page here along the coast, which quite often happens. This drives through Coriolis effects and so on, and Ekman stuff, that flow into or out of the fjord at the surface and a corresponding flow at depth. and you can do some calculations. You can do some sort of scaling stuff, and you can work out how the magnitudes of these two circulations scales with the geometry of the fjord. And within an estuarine circulation, it's roughly proportional to the cube of the depth divided by the length of the fjord. So that's assuming that you've got fresh water here, salty water here at some constant salinity, and you're just trying to exchange the two. And I can point people towards the places where this comes from if they're really interested in it. So this works very well in short but deep fjords, whereas the other circulation is determined by works very well in wide fjords. It works very well in long fjords, and it works very well if you've got the H coefficient has a much lower power, and it's the depth of the sill which matters, rather than the depth of the fjord itself, which can be considerably deeper. So Dave Sutherland and Fiamma Straneo have done some work on these two, and they've come up with a sort of classification of fjords into which of these circulations dominates. It turns out that Alaska, Svalbard, some of the small Greenlandic ones tend to be dominated by the estuarine circulation, driven by the glacier. But the big fjords in Greenland are dominated by this intermediary circulation. It's like 2 orders of magnitude larger. So most of the processes which are driving warm water into these fjords are mediated by essentially winds outside the fjord, rather than by anything the glacier itself is doing. So I think this is quite an interesting classification in terms of how we think these should respond to changes in the ocean. So for these guys, it doesn't really matter what the glacier is doing. All that matters is how the Christian is.
This is a dumb question from the knowledge, but if you have significant sea ice cover, does that affect the ocean becoming to any significant extent?
Well, not in this respect, no. Most of the atmosphere-ocean component is driven by pressure gradients at this point, which work through the sea ice.
So that seasonality in the second thing would then be driven by changes in atmospheric circulation, because you're really trying to get deeper waters in.
Yeah, so the seasonality in that is driven by, yes, changes in atmospheric circulation, and also changes in the depth of the change between the warm water and cold water layers.
See, lots like you showed before, I always have the feeling something's missing, and that's the third dimension.
Well,
So,
yes.
I mean, there's much more degrees of freedom how a circulation works in a fjord than these simple graphs, these 2D graphs imply. Because you
Yeah.
have, like inflowing flows, outflowing flows.
Oh, absolutely.
Or
These things
there
are.
seem to be some measurements that point into that direction. So
Yeah, I mean, definitely the wider the fjord gets, the more of these things start to happen, and if you get beyond the Rossby radius, you start to get Coriolis forced stuff going on, and that's you're not really in a fjord anymore. So to an oceanographer, a fjord is a sort of one-dimensional system, and it doesn't really have a width.
not even with Coriolis, just having the possibility to have two currents adjacent to each other, like left and right, instead of only one.
Yeah, it's yeah.
I think that's probably something that I don't know.
I mean, I'm not going to talk about that, but that is a thing which happens, and that varies very strongly from place to place. You need the unique topography of the particular fjord in order to look at that stuff. Really.
How do you get a current that goes like that? Aren't most of the circulations thermohaline driven? Is that caused by super stratified lots of glacial melt in one place versus another?
Could be sort of very weak Coriolis stuff. Yeah, but in general we're not an order of magnitude below the Rossby radius on most of these fjords.
So it's weak.
Yeah, it's not strong enough to be the dominant control, but it's is enough.
If you check the river on one side of the fjord, you would expect that this momentum is forward momentum,
Yeah.
which
It seems
would
like
really
it seems like it's
influence the whole circulation.
It seems like that's actually telling you something important about
It's probably not just
what's happening at the glacier, because that's going to be glacier force rather than ocean force, right?
the glacier just determines where the river comes out because geometry of the glacier.
Well,
If
yeah,
that's
I
in
guess
the
that's
center,
what
but on one side, then you kind of expect some circulation
I agree.
relating this down.
I agree. I just don't think you're going to see it without doing something near away from the ocean, because I think your densities are going to try and mix.
Yeah, yeah. I think anything where you got a circulation, a horizontal circulation, has to be driven by something local. Yeah. The sort of natural way for this thing to evolve is a vertical. Anyway, where was I? Before we go. So we've got this classification, which I think is quite interesting. So these guys, the temperatures in the fjord are probably not being influenced that much by what the glacier is doing. It's more of a meteorological phenomenon. Whereas these guys are essentially self-contained systems. They draw in warm water from the outside, but at a rate which is determined by the glacier itself. And so these guys are probably simpler to study in isolation, which is one of the reasons why I think Colombia could be quite interesting. Colombia has a very shallow sill, so getting water in and out of there, the system is essentially isolated from the outside world, which I think is interesting. So, if you want to know more about this stuff, there's a really good talk online by Dave Sutherland. He did it for APEX, which is the Association of Polar Early Career Scientists. If you search for, you can write down that delightful URL if you like. I couldn't find a better one. Also, there's a paper he and Fiamma recently published. It came out in the last couple of days in JGR Oceans. I started reading it last night, and I think it probably says more about the quality of dinner last night than the quality of the paper, but I did fall asleep while reading it. So it is quite dense and oceanography heavy, but there's some really good stuff in there, and I would recommend that. The talk is a lot lighter and for a more glaciological audience, so if you want to look at that, go for it. So the first thing I would say I want to ask about this is how transferable is knowledge between these two types of fjord? Do we need to start thinking of these as completely separate systems? Can we, we have a tendency as glaciologists to study a single glacier and say, well, this applies to everything. That's probably not true, but there are probably certain universals that we can translate between these two types. And how much of that there is one question. The other question, of course, is how much is this classification enough? Can we just say, all right, I'm going to study one of these estuarine fjords, one of these intermediary fjords, and then study how much, assume that we understand the two types. And then finally, how can we easily identify the type of fjord? These estimates come from when David Fiamma produced these estimates of these fluxes and did this classification. They were basing this on some quite detailed oceanographic work. We don't always have bathymetry. We certainly don't always have actual CTD casts and things. So if we think these processes are important for the glaciers, we're going to want to identify what's going on in the fjords. And if we want to identify what's going on in the fjords, we do need to get a classification going. So we need to find something remotely identifiable, which will tell us what we're dealing with. So I'm going to move on now to talking about undercutting, which I think has been alluded to a couple of times today, particularly from Doug. So if we're melting at the front of a glacier, what is that actually doing to the glacier? What's the effect that's going to have on calving? And this graph has also come up a couple of times today. This is from a paper of mine. Essentially what this is showing is how the change in I can't remember which particular kind of stress this is. Does anyone know? I think it's deviatoric stress, but I'm not sure.
I asked you when I was editing this paper.
Yes, you did, and I think I remember it was one, and then I changed it to the other one. So,
I think it's the deviatory. No?
yeah. So, well, essentially, what we're showing here is these glaciers are all the same thickness. I think it's 300 meters, and these are different water lines. And this is the stress field near the front of these glaciers as you undercut a notch here into each of them. There's no, as glaciologists, we like to do this vertical stretching thing. There's no vertical stretching on this. This is the actual shape of these stress fields. And what you can see is, or possibly not, is that you get an increase in the longitudinal stretching inland at the front, driven by this block. And sort of the main result of this paper was that this increase in longitudinal stress was linear in the size of the undercut, but with a reasonably large large multiplier. So typically, a undercutting by some distance would have an increase in stress, would essentially move the stress field backwards by an amount which was 3 or 4 times that amount. And the sort of conclusion, the speculative conclusion that I drew was that this meant that undercutting would drive calving at a rate which was some multiple of the amount of calving. I can see some.
H is the water line.
Sorry, H is the yes, it's the water line as a proportion of the ice thickness. Thomas?
I have your paper open. It says comparison of first principle Cauchy stresses.
Nice one. First principle Cauchy stresses for anyone who cared.
Is this a viscous stress?
Yes, so this is a Glenn type, n equals 3, which apparently it might be. So this is entirely viscous. There's no elastic component going on here. Also, this is a completely diagnostic simulation. There was no time evolution going on in this. I just sort of removed sections of the domain and calculated the stresses. Sue Cook took this and ran with it a bit on her model of Helheim. And what she found was that actually that diagnostic assumption wasn't that great. And if you keep the terminus fixed and do this, then it sort of evolves in that straight line, which is slightly less straight than the line I got, but her model was a lot more complicated. But if you allow the front to deform with this stress field, this effect more or less disappears because the front responds to that undercutting in some way. I have to admit, I don't really understand this result. My intuitive understanding was that if you were getting stretching as a result of an undercut, that would sort of bring the front even further out and compound the effect. But that's not what Sue found.
What is the displacement in the stress field?
So that's that was, well, if you read my paper, essentially the measure. So the argument I was making was that if at some point you have stress conditions which would lead to failure somewhere within the material, and what you want to do is look at a perturbation and then find out where those particular stress conditions move to. Does that make sense? So this is effectively how far you've pushed back the stress field by undercutting.
So if there are some other parameters in there that help you locate where
Yeah, I think I was looking at waterline stresses because sort of as implied by Doug's carving law, but the effect is fairly robust against where you do that. I mean, the numbers change, but the qualitative effect is still there.
So, Martin, you're arguing you get bigger icebergs when you undercut. Is that what I'm understanding?
Yes. So, well, That was what I argued in that paper. I'm not sure I'm arguing that anymore, but
That's what you were arguing.
that was what was argued. But yeah, as a result of Sue's results, I'm not so sure about that anymore. I think something interesting is happening when we do this in a time evolving simulation, which I don't fully understand. Thomas.
One catch here might be that basically the damage is not taken, it's instantaneous basically by the night habit of balls. So if you had the damage earlier by undercutting and changing the geometry, thus bringing basically the crevasse depth line pushing in.
Yeah,
We
that's
don't account for previous damage per se. That's what Sue said more or less.
yeah, that's
So her idea was to basically also include transport of earlier damage because the undercutting has changed.
yeah. Yes.
Does this make sense?
I don't know. Maybe. Christian.
I asked that paper, but my guess is the glacier turbulence tries to get away from its state of high stress,
Yeah,
adjusting its surface.
yeah. I just
think
don't
this
see
is what
why.
we see here.
Well, so my intuition is that the glacier's surface should stretch more. I mean, it is under tension, so it should stretch more, and in doing so, increase the size of the undercut.
Yeah, but if you adjust the surface in a way that it stretches less.
Yeah, but that's not the way the stress field is. So
But if you stretch more, it changes the surface more.
yeah, I'm just not sure why it's doing it in this direction rather than the direction of increasing. But yeah, I would have to dig into some actual simulations, which I haven't done. Christian is still looking confused.
So to go back to the stress field, labeling this, if when so now you reach the criterion somewhere, what is the piece of ice you should be breaking off actually look like? Because you said that the stresses are greatest at the waterline. Should you be like dropping bits off from above the waterline?
No. I mean, this is where we're assuming that the condition is somewhere back here. I'm not just talking about this little bit falling off.
Right.
It's these stress disturbances go way back, and Sue was looking at Helheim, which generally calves with an aspect ratio of sort of somewhere between 1/2 and 1. So you're quite a way back from the front at that point. Anyone else want to ask anything about undercutting? So one thing that sort of occurs to me from this is that the diagnostic simulations sort of they essentially imply a world where your melt rate is much faster than your deformation rate. You're producing these undercuts much faster than you're actually deforming the ice. Whereas Sue's simulations seem to have taken place in a regime where the deformation is fast enough to account for that. So one question is, on what timescale does undercutting affect the stress field? Can we identify how fast you need to be undercutting before there are significant changes in the stress field, and what the scaling of those two parameters is with the size of the glacier system? Another question is, how does this undercutting business work in 3 dimensions? Which is going to be much more complicated, particularly if we're seeing very localized melting. Doug showed these notches where undercutting has cut back into the front of a glacier. That's obviously quite a complicated 3-dimensional system from a stress perspective. So it would be interesting to see some studies on that. So finally, I want to say a little bit about ice shelves. And with this, I'm not really an ice shelf expert, so everything here is more questions than answers. So the first question I had, which I thought the answer to was no, was do ocean temperatures directly affect tabular calving? And I was pretty convinced the answer to this was no. And then I saw Jeremy's talk last Monday, where he showed a process by which small cracks, either small dents in the bottom of a an ice shelf either grow or shrink relative to the ice shelf thickness, depending on what the melt rate is. And these led to necking, and I'm sure Jeremy can explain it better than I can. But essentially, these led to, you can trace these depressions forward through an ice shelf, and you end up with them supposedly reaching full penetration when they get to the end. So I think the answer might be yes now, but I'm not sure. I would like to hear if anyone has any objections to what Jeremy was saying, or if I've completely misrepresented what Jeremy was saying. Moving on from that, though, this is a figure from a paper of Olga Sergenko's recently, and this is, the red color is, these are the depths of melt channels along the bottom of an ice shelf, and a lot of people have noticed these sort of things recently, that rather than having a big sheet of water moving beneath an ice shelf, the melt is at least partially channelized, and we see a really quite complicated pattern of stuff going on here. And I think it would be really interesting to know how this kind of structure affects the stress regime in the ice and leads on to calving stuff. So I guess the question based on that is, do melt channels have an effect on calving? And I don't know if anyone has an opinion. Knows anything about this? And I think that's my final question then, is not really about the effect of oceans at all, but we have this regime of calving where, I don't have a picture of this, we have a regime of calving where we look at ice shelves, and that appears to work on a very, very different physical basis to the regime we see on grounded calving. So I think the question of how we smoothly transition between those two, and possibly other calving mechanisms which dominate at the grounding line, is one that we need to look at. So I didn't make a conclusion slide because I was doing all this mostly at lunchtime. So I will throw